All right. So our speaker today is Philip Welch, who's a professor of pure mathematics at the University of Bristol, and one of the rare mathematicians who proves a lot of theorems that are of philosophical interest. He's known to mathematicians for his work in set theory and to philosophers for his work in modal logic and especially truth theory. It's a pleasure to have him today as part of the AFI project, and he's going to be talking about global reflection principles.
Thank you very much. Of course, a special thanks to an absent friend, Peter Koellner, for inviting me here today, and I sorely miss him. It's, of course, quite understandable. I've been partly pushed down this path of thinking about reflection principles by Peter's work, and I really agree with a lot of the things that he has to say, but not with everything, as you'll see today. It's a great pleasure to come here. It's a lot warmer than Bristol is. I was just saying to Mark here, I put in Fong Auditorium Broylston Hall into Google Maps just to find out where it was. This was at Heathrow Airport. And it came up with the university in Budapest, actually. It was a little flag, and so I did it again, and it was still Budapest. Well, Buda, actually. And so there's some glitch inside Google Maps that links this hall to the university in Budapest. But anyway, the plane went in the right direction, so yeah. I sometimes offer a small cash prize to people who can identify this picture. It's a detail. So it's a mirror, of course, and that's why it's apposite for reflection. So I'll let you know at the end. Another person who's influenced me a lot in this particular direction is Leon Halston, who's a colleague and friend in the philosophy department at Bristol. And we're writing a joint paper called Reflecting on the Absolutely Infinite, which will, I suppose, be ready at some point or other. But it's also on the more philosophical sides of the themes today. So this really is, in essence, joint work with Leon. So the structure of the talk. The first part, there will be reflection principles will be introduced and gone over, and I hope you'll bear with me. I hope to go over those slides fairly quickly because the material is quite standard. It does have rather a lot of symbols on it, so you might think things are going past rather quickly, but these are really just for motivation to talk about reflection principles as a whole. And I'm hoping that most people understand the motivation, at least for reflection principles to some extent. So after that first part, there is a section on set theories of Ackermann and Reinhardt. I think just to backtrack slightly, when, as I said, what got me going was to think about something that Peter had said in, I saw an early draft, well, a draft or preprint of his paper on reflection properties. And in that he talked about delineating what kind of reflection properties might be possible, and he gave very plausible bound on the kind of large cardinal strength that the intrinsically motivated reflection properties could possibly have. Of course, it depends upon what you mean by intrinsically motivated. So, given the slogan that he was saying that reflection principles are going to be limited by this particular large cardinal, which was consistent with V equals L, he laid down a challenge at the end of the paper that said, can we come up with reflection principles that will transcend this barrier and perhaps give us large cardinals? And so I was thinking, when I saw this challenge, I thought, surely this can't be the end of the story, right? That reflection principles are just those that are consistent with V equals L. And I started thinking, well, there are various large cardinal gadgets, so things called subcompact cardinals, which give us some kind of reflection principle at a sort of third order level. I was thinking, well, if you could apply these ideas to V, you would have perhaps some third-order reflection principle. But then I realized that these kinds of things were far too strong, and really what one would talk about is something more like extendable cardinals. And these were introduced by Reinhardt, at least in print in the early 70s. And so when I've talked about this subject before, I've heard people just say, oh, this is just extendable cardinals. This is sort of old hat. So somewhat chagrined, I went off to try and analyze a bit further what Reinhardt was doing. So this caused me to look back at the set theory that Reinhardt used in his, investigated in his thesis, that of Ackermann. And I really think that the kind of Ackermannian spirit pervades most of Reinhardt's papers. So I want to say a little bit about the background of this Ackermann-Reinhardt set theories, really just to get some distance from them, right? Because I don't think that what we're proposing is in the Reinhardtian spirit, right? Something different from that. And part 3 is sort of, for me, the meat of the talk. It's the principles that we want to introduce. Okay, I think I'm sure this lecture has many faults, but one of them is that there are far too many quotes actually up on the slides and appeals to authority in this manner. Well, I may talk about this one later if there's time. So here are 2 quotes, usually brought up when people give talks about reflection principles. The well-known quote from Cantor, the absolute, it can only be recognized, but it can't be known. Also, cannot be even approximately known. And Wang's logical journey is Gödel philosophy is also many quotes. You quote here from Gödel: the universe of sets cannot be uniquely characterized, i.e. distinguished from all of its initial segments by any internal structural property of the membership relation in it, which is expressible in any logic or transfinite type, including infinitary logics of any cardinal number. Well, historically, reflection principles are associated with attempts to say that no one notion, idea, or statement can capture our whole view of the universe of sets V. I'm thinking of V as being this union of the levels, the ranks of V alpha, going back to von Neumann and Romanov, where ON here is the class of ordinals. So that no one idea can pin down the universe of all the sets has firm historical roots, as in the last quote from on the previous slide. So indeed, once set theory was formalized by the first-order version of the axioms and the schemata of Zumelo, with the additions of Skolem and Frankel, it was seen that reflection of first-order formulae are when expressed in a first-order language that hold in the whole universe V with epsilon, actually reflect down to some initial V beta. So here one has Montague-Levy, first-order reflection. One takes any formula phi in the language of set theory with epsilon, and formula by formula we can prove in ZF that there are arbitrarily large beta such that you take any parameters from V beta, then the truth of phi of those parameters is reflected precisely by the truth of phi of those parameters when the formula is relativized to V beta. So this is actually, this is a theorem, right, of ZF. So, but far from perhaps being an epiphenomenon of ZF axiomatization, one might interpret the fact that the axioms of infinity and the axiom scheme of replacement are actually provable from the remaining axioms of ZF by means of this principle R0. So this indicates perhaps that reflection is an integral part of our view of the universe of sets, at least as far as we view that universe with our ZF spectacles on. So it's the main contention of this paper that a global reflection principle, when taken as an integral part of our view of the universe of sets, enables important or even necessary, perhaps, principles needed for current set theory, and indeed the modern view of that universe. So indeed, by formalizing a sigma n satisfaction predicate for an appropriate class of sigma n formulae, just call it FML sub sigma n, it won't reoccur later, we have still the current statement that's there in ZF, that there is actually a class closed unbounded in the ordinals such that we have reflection on points in that class. So informally, one could write for any beta in Cn, V beta is a sigma n substructure of V. Okay, so the story of how one arrives at the series of cardinals, inaccessible, Marlowe, and so on, is well known. I don't really want to retell it in very great detail here, but here are some of the pertinent points. And these are obtained by reflecting on normal functions f from the ordinals to the ordinals as having regular fixed point. This is in the work of Levy and Bernays, and thence to indescribability properties expressed as sentences in higher order languages. So this is well known. However, the global reflection property we proposed is actually much closer in the final analysis to the notion of something like an I-extendable cardinal, which was first introduced by Reinhardt. So to go through the lines here, one talks about functions as having regular fixed points. One can have a reflection principle that's souped up from the one on the previous page, R1, by assuming that one has inaccessible cardinal points where one can reflect to here. One may then ask that this property f itself reflect down to cardinals, and this way one gets Marlowe cardinals. So the property of being a Marlowe cardinal, if one is quantifying over all functions over the universe, this is a second order property, and Bernays investigated this some more by talking about higher order properties, and one gets higher order indescribability cardinals coming out of the points where these higher order principles reflect to. And I want to emphasize the point here, just the only thing really about this formula here at the bottom, point of displaying it is, well, there are M alternations of quantifiers at the front, but there's a P in here which is a second order parameter here. And so the formulae with second order parameters, one can successfully reflect down in this way. Okay, so this gives us indescribable cardinals, indeed, of any order. Okay, Ackermann. So Ackermann in, I can't remember if it's 57 or 59, anyway, late 50s, in Mathematische Annalen produced a system of set theory which had a very different motivation from the Zermelo-Fraenkel viewpoint, I think. So what Ackermann did was he interpreted Cantor's famous dictum that by a set we understand any collection of definite distinct objects of our intuition or thought brought into a whole, as instead we must require from already defined sets that they are determined and well differentiated. Thus, the conditions for a collection to turn out to be a set only turn on that it must be sufficiently sharply delimited what belongs to a question and what belongs to a collection and what does not belong to it. So he wants to say what turns a collection of things we already know are sets into sets is that there is a definite criterion for whether something is in or out of that collection. And then he says, however, now the concept of set, which I think means the extensions of the concept of set, is now thoroughly open as to what that is. Okay, so the set theory, which I'm not going to list all of the axioms for, this was provided for a universe with extensionally determined entities, classes, class construction, essentially as a comprehension scheme. There were sets, as a set completeness scheme. A member of a set is a set. A subclass of a set is a set. This was all introduced in a first-order language with a predicate for sethood, whether X was in V. The main differentiating principle was, if you want to, you can just read the English line at the top, it's formalized somewhat below. If I've got a collection of sets, and this has been definable only using set parameters and not using the predicate V, then X is a set. X is in V. And it's a formal version of that below here. If X is in V, and for all t, the formula theta, which must not have the letter V in it, right? If theta holds of X of t means that t is a set, then there is a set in V such that the members of Z are precisely those things, such as theta xt. So theta for us is defining a collection of things that are known to be sets, but it doesn't refer to V, the universe of sets. And this is the important point for Ackermann, is that the notion of concept of set is not determined, but we want a method for sharply delineating collections of sets in order to build sets. And reference to V would make that sharp delineation fuzzy. And indeed, Reinhardt later, whilst he was working from the premise that Ackermann considered that the concept of set itself as not sharply delimited, surmises that the intuition behind Ackermann's principle is that a sharply defined collection of sets is a set, and that the property T is a set such that theta xt, this is independent of the extension of the concept of set, but nevertheless gives a sufficient condition for a collection to be sharply delimited. Now the Ackermann quotation continues in the Mathematische Annalen, it's somewhat in paraphrase. The Cantorian definition is intended that a collection should be investigated. Sorry, in the Cantorian viewpoint, the Cantorian definition, it's intended that a collection should be investigated only in a case-by-case basis as to whether that collection represents a set or not. And it is not meant that it is determined in one fell swoop, mit einem Schlag, says Ackermann, for all classes, whether they're sets or not. We therefore see that a collection is not sufficiently well differentiated if it is defined through its relation to the concept of set. And that's why the letter V must be absent from the defining theta in that principle there. So the development of Ackermann's theory, just to say a little bit about this, Levy and Vaught fairly soon took up they added to A foundation, which had not been mentioned by Ackermann, and this proves the existence of classes such as the singleton of V, power class of V, PP, V, and so on. Levy showed that this theory A star, this was actually conservative over ZF in the epsilon language. So if A star proved some sigma from the language of Z theory with its quantifiers relativized to ZF to V, then ZF proved it too. And Reinhardt in extended piece of work in his thesis, which appeared in the early 70s in the Annals of Mathematical Logic, proved that this was the converse as well. So that actually Ackermann is conservative over ZF here. In the final chapter of that published paper, Reinhardt expands on these ideas and says that if this is so, then the collection of all sets V is not sharply defined, and that there could be other V prime, which could also serve as the collection of all sets, but differ in extension from V. In the closing extensions, he extends this theory A star to an A plus, which includes suitable schemes and an axiom that with V being a subclass of V prime would together prove that V was a member of V prime. So we're using the language of set theory about things that we would, perhaps ZF set theorists would normally think of as classes. Okay, so referring back to these systems of Ackermann, then he entertains precisely the possibility of a hierarchy of such potential universes Vn, each Vn being a member of Vn plus 1 for finite n. Then a slide just to mention something else. When Reinhardt looked at, in a paper in Fundamenta Mathematica, on some systems of Schoenfield and Powell, and he relates these again to Ackermann Z theory in more or less the same kind of terms. Schoenfield gave a very informal view of set development, and which he thought of as V as being actually existing sets, but that there were imaginable sets that one could have taken some sets and constructed from, and essentially came up with a sort of stage progression idea of evolving sets. And Ackermann gave some, Reinhardt gave some formal precision to this and came up with a principle which one can see is very similar to that Ackermann principle, that if you've got X being a subclass of Y and Y is something imaginable, suppose that X was definable only using parameters from V, the world of sets, then again X was a member of V. But I shan't say anything really more about that. But again, the flavor of what he was trying to do in that paper was to relate those systems again to this Ackermann-style set theory, where one has these different potential candidates to the universe V. So, a long quote now from Gödel. So all the principles for setting up the axioms of set theory should be reducible to Ackermann's principle. The absolute is unknowable. The strength of this principle increases as we get stronger and stronger systems of set theory. And the other principles are only heuristic principles. So the central principle is the reflection principle, which presumably will be understood better as our experience increases. Meanwhile, it helps to separate out more specific principles, which either give some additional information or are not yet seen to be derivable from the reflection principle as we understand it now. So Reinhardt's perhaps major paper, which is read by philosophers of set theory, is a 1974 paper in the UCLA Logic Year volume, or second volume. And he discusses there at length first and higher order principles. And the discussion there, he lets omega denote the class of the Cantorian ordinals, and V, again, the Cantorian sets. And after a discussion of first order principles that urge us to go beyond V and take the latter as a set, he states one heuristic principle. And again, one can see something of the Ackermannian principle here. One can take sets x, y, and v, and if theta is to hold of x and y, if and only if theta holds when relativized, when one takes the quantifiers, it's all first order, takes the first order quantifiers and relativizes them to the to v. So it's asserting that any first order statement about v, or objects in v, holds in a or the projected universe. He uses this phrase quite often about a projected universe beyond v, or an imaginary universe, or one inhabited with imaginary sets outside of v, and in which v appears to be, as it were, just a rank inside this projected universe or realm. So he's imagining the possibility of getting outside of Cantor's V and thinking of ordinals such as omega plus 1 and further sets. Again, I'm using the scare quotes kind of advisedly here, such as V omega plus omega. So he says he thinks of this as akin to virtual displacements in physics and as a not inconsistent imaginative foray. So he's considering a realm of projected objects, hence my use of the scare quotes, and he wants to adopt Cantor's theory of V, which is V sub omega, as still holding in this extended realm. He says at some point in the paper he wants to mitigate the sorrow of positing things beyond V by saying, well, at least we have the universal application of said theory even to these new imaginary things, whatever they might be. So he takes the axioms of ZF, but in a language with the letter V and omega added as syntactic constants for these Cantorian universe and the class of ordinals, and he assumes the theory of V sub omega is applicable to this projected realm, and he arrives at this scheme S2. And as I've said, this is similar to Ackermann's scheme. And he then says the theory of ZF plus S2 plus V equals V sub omega is consistent relative to ZF. And after discussion of Bernays' second order reflection property, he remarks on the failure of this to carry up to third order. So I emphasized at that long higher order statement at the bottom of probably the third or fourth slide, this just had a second order parameter in. If you try and squeeze in third order parameters in that place, it becomes inconsistent. So if we are to consider, he wants to kind of then expand the considerations that led into S2 to take into account second order objects, so classes over V. And he says, well, if we are to conceive of them merely as collections, if we are to consider the class set theory, then we have classes distinct from sets. However, if we are to conceive of them merely as collections, and this looks like a distinction without a difference, he then remarks on the view that once one allows further ranks of classes and classes of classes beyond V omega plus 1, it looks simply as if one has stopped too soon whilst collecting together all the sets. And moreover, the classes threaten the universality of set theory. Okay, so this brings him from S2 to this principle S4. So one sees the similarity here with S2. One is now introduces some classes here P into the language, and the formula theta is now has its quantifiers restricted to the power class of V. But again, it's the same sentiment that the truth value of this theta about x and y and p, when relativized now to the power class of V, this should be the same as theta of x and y, and then this projected extension of this class P by some j, whatever this j may be, this agent of projection. So he extends the theory of ZA, which was the conjunction of those three there. Again, this is named ZA, Z is Amelo, again A for Ackermann, because it's inspired by the same by Ackermann's principle again. So he extends ZA to allow for this unary function symbol, and this is allowed into the comprehension scheme. Theta relativized to PV is, as I've stated, has its quantifiers so relativized. And now the conception is that we have this formally projected universe in which V is a set, and the proper classes are identified as the projected classes JP, but they're intersections with V. So they're the projected subsets of V, if we're thinking of now V as a set. So there are these projected classes, imaginary sets, and we formulate a hierarchy, V omega plus 1, etc. here. So he's arguing for a formally, and he uses this notation quite freely in the paper. He argues for formally projectable realms, which he says V sub lambda, for some lambda considerably bigger than omega, with a corresponding V lambda prime, and these may be related in the form of this last line here, that there is some J that is sending the classes, and then these imaginary classes of classes and classes of classes, and so on, up to stage lambda, built over V omega, up to a similar hierarchy built over some, well, J of omega, which he calls omega prime. So there is some hierarchy on the right, V lambda prime, built over this V omega prime, where omega prime's J of omega. And we have this preserving map, preserving the formulae of the kind at the top of the slide there. And as I've said, this last bullet point just emphasizes what I'd said before. In all of these realms, he wants set theory to be applicable. Right? It's just we shift our point of emphasis from V to some V omega to some V omega prime, but in all of these worlds, we have that set theory is applicable. He wants our mathematics of our set theory to be constant through these different realms. So set theorists probably on the whole do not read Reinhardt's paper so much these days. What they're familiar with is a notion of extendable cardinal, and there's a formulation of Reinhardt's definition, and this is perhaps given by Silver, and this is given here in this definition. So we say a cardinal is eta extendable if there is some non-identical J sending V kappa plus eta epsilon, let's say a predicate for V kappa, into some V lambda plus eta epsilon with a predicate there for V lambda. So the idea again is that we can send a stack of ranks above kappa over to a stack of ranks above lambda. And here we would be talking about first-order elementarity in just in set theory, perhaps with the predicate letter for this, the v capital V lambda. The point of me stating it like this was that because normally in the definition of extendability, one would drop this last predicate, v capital V lambda. It wouldn't be necessary. Stating it like this, one can see, or Levy first showed, I think, with perhaps eta being 1, but also Reinhardt also showed, is that one can justify Ackermann's theory A with foundation because we have here a model for it here. So the kind of bringing it down into the realm of set theory, the model theoretic component, or the model theoretic part of this principle S4 that was introduced on the previous slide are these eta extendable cardinals. And at times, Reinhardt suggests motivating such extendable cardinals by appealing to resemblance between parts of V. I think it's kind of it's interesting perhaps to see where this ended up. So Reinhardt and Solovey, with a co-author in the audience here, Aki Kanamori, produced a later paper looking at various large cardinals and motivations for them. And in there, resemblance was used as a possible appeal for looking at relationships of this notion of extendability between initial parts of the V hierarchy here. And so there is none of the kind of Reinhardtian discussion about formally extending V into different realms, and what's left is perhaps this motivation about resemblance between parts, and there's even a statement where I don't know whether this was a wistful or wistful statement left over from Reinhardt's thinking about these previous motivations, where he said, but this was not the original motivations for these principles. So I think he was alluding there to the previous papers. Okay, so to turn a little bit to Peter Koellner's paper, he mentions two problems for Reinhardt. There's a problem of tracking. There's a problem of extension to inconsistency, which I won't talk about today. But I will mention a bit about the tracking. When Reinhardt sets up these potential universes, V0, member V1, member V2, say, which can be different interpretations for our notion of set, he introduces constant symbols, say Cx for each x, which is in the power class of V0. But he then sets up a sort of reinterpretation functor. I mean, that's my word, not his, but it's a function g, which is such that if you take some x, which is a set in V0, then g of the constant symbol Cx is still just x itself, so reflecting on the fact that if there's any j going between V with its power class, it's the identity on things in V. Whilst g of Cx for some capital X there is going to be some x tilde in the power class of V1. And the problem that Koellner's alluding to here is that there is one of tracking. There's some kind of intentional notion going on here. And the problem is we're taking this intentional notion and we are looking at an interpretation of the constant symbol Cx over V0, and we then have to relate it to one in V1. And how are we supposed to carry this intentional interpretation forward? Or are there even enough intentions over this power class of V0 for us to actually do this? So there are various problems, and again, also about the modalities of truth in these different universes that Koellner points out. And again, I don't want to talk about those here. Also, in Peter Koellner's paper, he looks at very strengthened reflection principles due to Bill Tate, higher order principles, again, but as I've said, these can't contain third order parameters by Reinhardt. And he showed that all of these are weaker than so-called first omega Erdős cardinal, kappa omega. This is a cardinal which in effect guarantees that for any first order structure which contains the cardinal in its domain, there's an infinite sequence of good indiscernibles for this structure here. So the universe is sufficiently rich in sets of indiscernibles that it can find for any structure based on kappa and omega sequence of indiscernibles for that structure. And this is something that's entirely consistent with the constructible universe. If there are such cardinals, a simple well-founded tree argument shows there are such cardinals in any such cardinal in V is such a cardinal in L, basically because one only needs an omega sequence of indiscernibles. One only has to search through for a path through a tree, building longer and longer sequences of indiscernibles, and one will find such a path if that tree is ill-founded. One can define that tree inside L. But that only works for ordinals such as omega that are countable in L. As soon as you take an uncountable in L ordinal there, in place of omega, the argument breaks down. And in fact, you get something that implies that there is an embedding of L to itself. So one gets a large cardinal property if you replace that omega by the omega 1, either of L or V in this case, in here. So the principles that Peter Koellner looks at and analyzes in the paper, he shows are all weaker than this cardinal here, and he identifies, and I think quite rightly, this as a good test cardinal. It's a good place to draw the boundary for possible reflection principles, simply because this little model that you can get from these indiscernibles here, one could find a nice small countable transitive model which has got embeddings to itself from these omega many indiscernibles. And he has an argument that says, well, if one had reflection principles, one would have all sorts of indescribability properties over the ordinals inside this model here. Sorry, I'm not making that terribly precise, but he identifies this Erdős cardinal, and he lays down this challenge. He says, what we want, or the challenge is to find some intrinsically motivated reflection principle which will go beyond this kappa omega barrier. So he sets up kappa omega as his target. Okay, so the intrinsically motivated, and what he means by that are those kind of motivated more or less by the pure iterative concept of sept. The intrinsically motivated reflection principles are to date all consistent with the view of the universe as being L, the constructible universe. So they are, again, it's my phrase, intra-constructible. So, but these are all motivated on a sort of logico-syntactic level. So what we want to do, if we want to go beyond this, is to find some stronger extra-constructible reflection principles. And those that generalize Montague-Levy principle are not up to the task of providing those principles that set theorists commonly use these days in their view of V, right? Namely some large cardinals. So we want to have some kind of reflection principle that gets us beyond large cardinals. And Peter gives a very, as I said, coherent argument as to why the intrinsically motivated ones are going to be always stuck inside the constructible universe. And indeed, this perhaps reflects the age in which these principles were first investigated. So what we want to do is to find some kind of global reflection principle. So we want to start somewhat afresh. So what we want to do is, or what we don't want to do, is to consider interpretations of V temporarily as some V kappa, or to think about intended or suitable domains of sets. This is rather complicated and leads to these kind of tracking problems that I mentioned. So we abandon hope of a strong internally defined reflection principle, meaning one defined using formula by formula reflection, perhaps in some higher type language, using this iterative concept alone. So we're going to seek a more global principle of reflection that is not purely motivated by logical or syntactic considerations, by a more holistic view of the nature of sets and class theoretic activity. So the view that we're going to exposit does not contradict the iterative concept, but maybe you can be seen to extend it. So we're going to take the viewpoint that the mathematical objects of our discourse are all sets. Thus, V and on, or the class card of cardinals, these are not sets. So these are not mathematical objects. These are the absolute infinities or inconsistent multiplicities of Cantor, depending on when he was writing, or perhaps even who he was writing to. We're going to swallow the Cantorian pill that there are two types of objects: the mathematical discourse, or set objects, and then there are the absolute infinities. So we're going to gather together the collection of all of these absolute infinities into script C. Okay, so this is admittedly a somewhat ineffable collection. And we don't have absolute or final knowledge about what these are, nor about what the structure of V epsilon script C is. But what we could do, if we wish, is tell a mereological story about the whole mathematical universe. We think of the sets as the solely mathematical objects. But sets with the absolute infinities are parts of just the whole realm of discourse, which itself, again, is not a mathematical object. We take C to be the collection of all absolute infinities, or, if you want to use the words, proper classes, or certain pluralities of sets, if you will. But C contains all the possible parts of V. And we may allow ourselves to talk about pluralities of such classes, or of such parts. Okay, so we then consider the whole of this constellation, or this global realm, V epsilon C, and we use the same membership relation epsilon in the usual sense. We'll have X a member of Y for X and Y sets in V, but also we'll say X is a member of capital Y for any Y in C. So we'll avoid this Bernoulli's use of a second membership relation. I'll try and reserve these uppercase letters X and Y and Z for parts of V, and loosely use epsilon again, hopefully without danger of confusion. If I just say X epsilon script C to mean capital X is one of the parts that's in C. So this then is the realm of Cantorian discourse that properly encompassed V. So again, this is the realm of mathematical object discourse and the collection of these absolute infinities. So we're going to assert a global reflection principle about this structure. So again, in a sort of pre-formalized stage, the evolution of set theory, maybe if you want to say it's Cantorian period, C would have had some potentialist flavor. examples of absolute infinities in C to hand would have been restricted to those definable as extensions of predicates that were probably not sets, as Cantor had in fact realized, or Burali-Forti demonstrated. Initially, we don't have to assume that this C is closed under first-order manipulations, which we would if we were to assume V epsilon C to be a model of NBG, which we might be tempted to go straight towards. But from the outset, we don't necessarily assume this is an NBG model. On the other hand, if we consider the finite axiomatization of NBG by Bernays, in particular the finite collections of operations on classes which it embodies, then these operations seem unproblematically to lead from absolute infinities to absolute infinities, so from elements of C to C. We'll see a little bit more about this in a moment. What we're going to think of is that this whole realm, the epsilon C, is just simply, and I'm going to use the word reflects, is going to reflect down to some initial part. So V together with its parts will be reflected down to some V kappa together with its parts, which we would commonly call V kappa plus 1 here. So we might think of this V kappa, epsilon V kappa plus 1. This is a normal domain with its parts, and perhaps it typifies or exemplifies the whole of the picture. So in the last bullet point, I want it to be a consequence of this picture. This is not the motivation for the picture. It's a consequence of this. It should be a consequence of this picture. That anything satisfied in it by a set X and a class X, capital X, is itself a reflection of something satisfied in the whole realm, VC, by X, and by one of the parts or classes of that whole realm. So some X tilde, say. And heuristically, what else could this X tilde be but just something that extends little x? It should be a part of the whole V that extends X, i.e. X tilde intersect V kappa should be just the same as X. After all, the picture is supposed to be that we are taking this whole universe and this reflects down to this V kappa together with a collection of all of V kappa's parts. It's a full reflection down to this point. I want to emphasize that we need all of V kappa plus 1 down there for this to have any strength. So let's express it like this in a sort of mathematical looking way. Is GRP0 is that there is a kappa in the ordinals and there's a non-identity J whose critical point is kappa, and J sends V kappa epsilon V kappa plus 1 up into V epsilon C. So here the subscript is denoting elementarity with respect to usual first-order language of L epsilon, but I want to throw in variables for second-order variable symbols. So it's kind of full second-order language, but with no second-order quantifiers, if you like. So second-order language L2 minus second-order quantifiers. And the E down there is saying that J is supposed to preserve elementarity in the following fashion. So you take a formula phi in this language, which has got variable places for sets little x, for classes big X. Well, phi must hold of x and x if and only if phi holds of J applied to those objects. J of x, little x, and J of big X. J of little x is the identity because the critical point of the map is kappa. So we have that J of little x is x. So this is equivalent to phi holding of little x and big J of x. So what else have we got in this picture? That J restricted to V kappa is the identity, and J is sending kappa up to ON. If we're assuming, as I always do, that the choice applies to sets in V, one can see then that we're going to have that the whole universe V epsilon will be a model of global choice. This is reasonably easy to argue. And included in that definition, of course, about J is that V kappa is an elementary substructure of the whole universe. But of course, J is saying much more than that. We can soup up the definition to talk about having unboundedly many such kappa in on, rather than different J's for different kappas, and there are unboundedly many such here. I shan't be talking terribly much about that, but it's a natural thing to ask for here. But we'll just consider GRP sub 0, this ostensibly weaker version here. Okay, why GRP 0? Why this? All right. Well, you can define in a very standard way a field of classes on the power set of kappa by looking at those x's such that kappa ends up inside J of x. Now the field of J, the domain of J, contains the whole of the power set of kappa. So it's just a yes-no question about whether kappa's in J of x or not. So this U then is an ultrafilter on the power set of kappa, and just by using very simple elementary properties about J. This is an ultrafilter, and you can establish other nice things that set theorists want. Additivity of this ultrafilter, it's non-principal, and again, one can use easy arguments to show that it's normal. So this U then establishes that kappa is a measurable cardinal, and we've already strongly gone outside L in that case, if there is such a J. And again, just a little argument here shows that, well, if we establish by this that kappa is a measurable cardinal, just V itself, without this script C here, is going to show, okay, for any alpha less than kappa, V is a model of, there is a kappa bigger than alpha, which is measurable. So by elementarity, this must happen below kappa, so we have unboundedly many measurable cardinals below kappa, and this reflects back up to saying there's unboundedly many measurable cardinals in V. So just, I think really it's, to someone very familiar with Kanamori's book, it's an exercise then with the definition of a Woodin cardinal to show, in fact, that there are unboundedly many Woodin cardinals, and indeed this kappa itself is a Woodin cardinal. So this slide here then gives you the kind of the extrinsic justificatory payoff for this GRP 0. Getting these unboundedly many Woodin cardinals gives us strong results about V. So results of Steele and Martin and of Woodin give us PD and give us projective determinacy, gives us full determinacy inside the inner model L of the reals. We have all these nice absoluteness results from having a proper class of Woodin cardinals. Woodin's shown this fixes the theory of the reals, it fixes the theorems of analysis, but it fixes also the theory of this whole model of R. If one has all of these Woodin cardinals, and there's a whole load of other stuff of Woodin's work about the omega conjecture and so on that is always prefaced by some kind of hypothesis that you've got these unboundedly many Woodin cardinals, or occasionally measurable Woodin cardinals in the universe. So this principle delivers for us all of these nice large cardinals that we want for these results. And again, just to kind of continue the U-Woodin kind of line a bit here is, you know, why should we be concerned about projective determinacy? And again, you would say that PD gives us something like a complete theory of the countable sets, much as something as PA is like a complete theory of the natural numbers. complete in what sense? In the sense that there are no examples of sentences about the countable sets, the hereditary countable sets, HC, that aren't decided inside that structure. If you assume V equals just the hereditary countable sets, and PD and the appropriate amount of set theory, ZFC without power set minus, the only independent sentences that we know about are Gödel sentences for this theory. So GRP0 proves this PD, ADL of R, and all of these other things. Okay, so let's go back a little bit towards this GRP0, and which we introduced somewhat informally. If you wanted to formalize this GRP principle, what might you do? So two options. The assertion that there exists a J as given. So on the first look, it seems like it's a third order statement. Right? We're saying that there is this connection, this J that takes classes over V kappa plus 1 and sends them up to classes in C. Right? So there is this map. I mean, J considered as a collection, as I said, is a collection of ordered pairs. First thing, element of V kappa plus 1. Second thing, a proper class. So it looks prima facie third order. But we can finesse this a little bit and just think of J as being coded just by a single class itself. It only, after all, has to connect the size of V kappa plus 1 many sets with classes from parts from C. So we could finesse little j as a big J here, thinking of a big J as a set of ordered pairs of Y in J of X. And now I've broken my own rule. Little x here could be a subset of V kappa. Right? So little x could be a member of V kappa plus 1. J of X will then be in script C here. Then in the old sense, J of X is just simply the section through big J here. It's the collection of Y's with XY is in J. And the measure U, for example, we can define easily. It's the collection of X's such that X kappa is in J. So just sigma 1 elementarity in the language and using the class variables here, this suffices to get the large cardinal properties out, if that's all you're interested in. So under this viewpoint, you're only obliged to reflect sigma 1 set variable, meaning the sigma 1 existential quantifiers are only quantifying over sets. So they're set quantifiers. The set variable existential assertions are sigma 1 that need to be reflected about the parts of V in the range of J are those that need to be reflected down to V kappa with its parts. There is no need to quantify over parts with a higher order quantifier, or indeed require them to be closed under certain operations. The usual kind of arguments, one can strengthen this to actually get sigma n preservation. Again, just in the first order theory, sigma n just using set quantifiers here. On the other hand, as I mentioned earlier, it would be natural to think of VEC as a potential in BG for Neumann-Wernheim's Gödel model here. We didn't say that it had to be. We just said that there was this J. Just to make this plausible, just to mention one or two facts of the Bernay's axiomatization here. This includes a number of statements, but the point of Bernay's axiomatization is that it's finitely axiomatizable. So he requires that we have the graph of the epsilon relation here. So this is, again, is a class of ordered pairs, which gives us the epsilon relation. We have the diagonal identity class here, as being classes. These have to exist, and these, I think, Cantor would have recognized as being absolute infinities. And just to mention two other typical axioms of NBG, they're statements of the form, for any classes A and B, there's a product class in cross P. Or perhaps more mysteriously, for any class R, there's a class S, which has the following property. It can reorder ordered pairs of ordered pairs that happen to be inside the class R. But in both of these cases, this is a for all exists. So this is saying for all classes there's another class. It's just a pi1, 2 axiomatization. So I think, again, one would say that if you went through each of these Bernay's axioms, you would say that these would undoubtedly take you from absolute infinities to absolute infinities. So it would look very naturally like this class script C is closed under the Bernay's operations, and that's enough to conclude that V epsilon C is an NBG model here. Another way perhaps of seeing this would be to insist that that J we had from the outset preserved sigma 1, 2 statements now in this full language. So if we said that we thought about J preserving statements of the form, there exists a class that's for all classes, so sigma 1, 2. If this was preserved from the junior realm up to the senior realm, and vice versa, that would automatically give us that the V epsilon C was an MBG. I'm just sort of playing with various possibilities here. If you wanted to formalize the assertion that J was a fully sigma 1n for every n elementary preserving embedding, one could add to the language, if you wanted, a ternary primitive relation symbol for second order satisfaction, and one would add axioms to say that, again, something rather familiar, that SAT hold of a code for a formula theta of the relevant kinds of parameters, if and only if V epsilon theta was a model of that particular formula. And you could then require that the embedding J preserve this satisfaction class up and down here. This would then give you a somewhat stronger principle, just as if you put satisfaction into NBG, you get a slightly stronger theory there. If you did this, then you'd conclude some more about V epsilon C. Actually, since V kappa with its classes is a natural model of Kelly-Morse, with the second order satisfaction principle, we get full second order comprehension in predicative comprehension carrying up to V epsilon C. So we'd have that V together with C is actually a KM model. Okay, so I think that there is little in our original Cantorian conception that would say that V epsilon C was even an NBG model, let alone a Kelly-Morse model. So the ineffability of the structure V epsilon with its parts gives us little to say about it mathematically. We've no guarantee that the parts of V are extensions of predicates in any particular language, but we might, however, as remarked above, being inclined to allow nevertheless that reasoning about the absolute infinities or parts of C may imply that it's closed under the kind of elementary operations required by Bernay's for axiomatization of MBG. Bernay's operations are indeed simple in form and lead from absolute infinities to such. Okay, so towards some conclusions. Is it a reflection principle? So what I'm adopting here is a kind of actualist stance. I'm not thinking of the universe of sets as being some kind of potential. There is no feeling at all here that there's some kind of Zamalian increase of domains as we go up through the ordinals, getting larger and larger segments of the universe. We have a given universe, Cantorian universe V, with a Cantorian collection of ordinals, omega. We think of the V part as being justified by the iterative concept of set. Of course, that does not justify the existence of such a J. So if we're going to adopt Peter Koellner's division that, strictly speaking, reflection principles must be internally justified by the iterative concept, then this, of course, falls outside. On the other hand, in discussions with email with him, he seems to think that he prefers the word resemblance, whereas he would like the word reflection to be kept to things relying entirely upon this internal or intrinsic kind of justifications. On the other hand, I don't think that these arguments by resemblance, that we may have some V alphas that may resemble in some higher order type some other V beta, I think this is more than resemblance. V kappa with its parts is not merely resembling V with its parts. The map J is a connection, is the agent, the means of actual reflection. It's reflecting our whole view of this. It's kind of Gesamtauffassung we have of this whole thing of V with C down to this V kappa plus 1. But what it does is avoid any of the kind of journeys that, or forays that Reinhardt used into these imaginative or projective realms. We don't have any difficulty about ascertaining what legitimate domains are. The principle just posits that the universe is so rich that it does reflect in this way to some such kappa. We're not talking about legitimacy of kappa in any way. We're not talking about using V kappa with its parts as some potential universe for any kind of discourse. We're just saying simply that it's there. So we don't have any problem about tracking intensions or extensions of predicates over V kappa up to some V lambda or some V itself here. So Gödel again. Generally, I believe that in the last analysis, every axiom of infinity should be derivable from the extremely plausible principle that V is indefinable, where definability is taken in a more and more generalized and idealized sense. So clearly, these GRP principles are taking that generalized or idealized sense very liberally when judged in the light of the strict iterative conception. But I think in the light of using the phrase again, this Cantorian-inspired Gesamtauffassung that we sketched above, they deliver a natural and satisfyingly rich universe for us. Okay, thank you very much.
These are just small, picky questions, not
Yes.
in any way deep. About your use of the term absolute infinity, that seems to fit very well enough the way you describe what C is to begin with. But when you talk about the possibility that it might be a model of the classes of NVG, you run into a problem that you seem to have not mentioned, and that is that those operations enable one to derive first-order comprehension. So among the classes are ones that correspond to sets that aren't absolute infinities at all.
Yes.
So that makes absolute infinity a somewhat misleading terminology when you do discuss the possibility that it might satisfy MVG or even Kelly Lewis.
Yes. I probably need to be a little more precise, I think, in what I was thinking of script C as, if you tell the mereological story, script C are the parts of V. So these may be sets, and these may be the absolute infinities. So I'm thinking of the script C as being, again, sets together with the absolute infinities. So this is all the parts of V.
I had another picky question. I'm not sure how to locate it on your slides, but on the paper it's page 11, where in typical reflections, if you have an equivalence, then one formula has its quantifiers relativized and the other one doesn't. But there isn't that, you say phi of small x big X with only a phi of j of x, j of big X. Wouldn't you want on the left a relativization to something like the power set of V kappa? Or if not, why not?
I'm thinking initially of this J as being rather simple. So I didn't want to say anything about quantification over parts or over any second order quantifiers in here. No, I think I'm thinking here in this phi. I believe this is the place that you were talking about. Here is this.
Yeah.
I'm thinking of that formula phi as just being in the first order language of set theory, but augmented with variables for these second order parts here. So I'm not, so the quantifiers in phi remain set quantifiers without being relativized.
My question was, wouldn't on the left side,
yes,
set quantifiers be restricted to V kappa? And if not, is there some reason why they wouldn't?
Yes, you're right. I mean, I've just presented this badly. I mean, I should say that this thing here on the left here, I'm thinking here of the truth value of this thing in V kappa, and on the right, I'm thinking of it upstairs in the whole structure.
Okay, well,
Thank you. Yes, this is bad presentation.